So let us do another example. The plate P is tied down so that the 0.4-meter long cords keep a 1-meter long spring compressed 0.6 meters when nothing is on the plate. If a 2 kilogram plate is placed, no here, if a 2 kilogram box, if a 2 kilogram box is placed on the plate and released from rest, after the plate is pushed down 0.1 meter, determine the maximum height h the block will rise in the air measured from the ground. So what do we have in this problem? We have a certain spring that is compressed by force because of these cords here. So if you look at your figure, you have 4 cords that are keeping my spring compressed because the unstretched length of my spring is 1 meter, while the cords will force it to be always if I don't put anything on the plate, the length of my spring is 0.4 meter, while L0 is 1. This means that if I don't have anything on the plate, delta L is minus 0.6. So it's compressed. Delta L, if you want, I will call it state 0. So delta L 0, if I don't have anything on the plate, equals to minus 0.6 meters. Now what happened in our problem, we have a block, we put this block and we compress it on the spring 0.1 meter down. Okay, so now since when we put the block we compressed 0.1 meter more, so I can say that this is my initial state. I pushed 0.1 meter down my system, and then I left my block. So if you want, this is the initial state, state 1. So this is state 1. And at state 1, what will be the compression of my spring? It was already compressed 0.6, and I pushed it down 0.1. So in total, delta L1 is equal to minus 0.7, okay, meters. Now, I will leave my block, I will leave my system, and the block will rise upward. The question is, what is the maximum height the block will reach measured from the ground? So my purpose is to find this height, h. Okay, so here I have an initial state and I have a final state. The final state is when my block will reach a certain height. So this is state 2. I will put it here. At state 2, what will happen? The spring cannot follow the block. It will go with it until reaching delta L 0.4 meter, delta L 0.6, sorry, because the length here of the cords, these 4 cords, will force the spring to stop at this level. So the spring cannot follow the block. So once my springs go back to 0.4 meter in length, therefore a compression of 0.6, the spring cannot follow anymore the block. The block will continue on its own until reaching the maximum height. At the maximum height, what is the characteristic for the block? When it will reach the maximum height, this means that its velocity here is 0. Okay, so this is state 2. In state 2, the characteristics are a velocity of v2 of 0, and for the spring at this state, delta L2 will be equal to minus 0.6 because the length here is 0.4, and delta L2 will be equal to delta L0 equal to minus 0.6. Okay, while at the initial state delta L1 is minus 0.7 and V1 is 0 because my system starts from rest. I said that my system starts from rest. So now I know the initial state, I know the final state, so I will do the principle of work and energy. If I apply the principle of work and energy from state 1 to state 2, what can I say? I can say that T1, which is the kinetic energy at state 1, plus sum of work between state 1 and 2, from 1 to 2, equals to kinetic energy at state 2. But since V1 equals 0 and V2 equals 0, so T1 and T2 are both equals to 0. So my equation will be reduced to sum of work from 1 to 2 equals to 0. Now, what are the forces that will do work? I have in a first stage, I have the work of the spring and I have the work of the weight. Okay, so here I can say that I have summation of work of spring plus work of weight equals to 0. Now for the spring, the work of the spring is half K times, what is delta L1? It's minus 0.7, but when I do square, the minus will cancel out, so 0.7 square minus half K delta L2 square, which is 0.6, so times 0.6 square. This is the work of the spring, and as you can see, it is a positive work because the spring was compressed and then the compression is reduced, so it will produce a positive work. Now, for the weight, since my block is going up and the weight is downward, then the weight will have a negative work, and the work of the weight is minus W delta Y, minus W delta of Y. Okay. Now, what is delta Y in this problem? So this is equal to 0. Okay. Delta Y is the change in vertical position. So at the initial state, this is Y1. What is Y1? It's 0.3. So I will write here Y1 is equal to, if I take the ground as my reference, equals to 0.3. And Y2, when I reach the maximum height, Y2 is equal to H. Okay, so I can replace in this equation delta Y by H minus 0.3. So delta Y is equal to Y2 minus Y1 equals to H minus 0.3. So now if I replace back in my equation, the only unknown is H. I can get the value of H. Okay, any question on this problem?
Dr. هيدي يعني mechanical energy conservation.
Yes, this is another, yes, you can, here you can apply, we will see conservation of mechanical energy next time. Here you can apply conservation of mechanical energy because you only have forces that are conservative, which are weight and the spring. And you will define conservative force next time. Okay, just one remark here, that you can divide your motion into two steps. Yani if they ask you, for example, what was the velocity of the block when it will leave the plate, then you can divide your cases into three steps. Step one, when the block was at 0.3 meter. You have an intermediate step where the box is here, and when the box will reach this position. At this position, the box and spring we will have separation between them because the spring cannot follow anymore the block. So at this state, you have an initial velocity for the block. Okay. So if they ask you what is the velocity of the block when it will leave the plate, you can apply the work and energy between state one and this state. And after, to find the maximum height, if you apply between this state and the maximum height, you can also obtain H. And this is a second method to obtain H. But what we did is easier because instead of doing it in two steps, I did it only in one step. Only if they ask what is the velocity of the block when it will leave the plate, I am forced to split it then into two steps. Okay? So if you want, let us find it. Let us find the velocity when it will leave the box. Just let me check your chat. we cancel D1 and T1 and T2 because at the initial state we start from rest, so V1 is 0. And at the final state we reach a maximum height, so V2 is 0. Okay? Now, if I want to find the velocity of the block when it will leave the plate, so I will add this question for you. Calculate V when it is leaving the plate. Okay, so what do I have? I have this state and this one. In this state, if I call this is state 1, V1 equals 0, and delta L1 equals to minus 0.7. If I take now this state, I call it 2, then V2 is equal to an unknown. I want to find it. So equals to, I don't know what. And delta L2 is minus 0.6. Okay. So if I want to apply work and energy between these two states, what do I get? Initially, my system is at rest, so T1 is 0. Plus, now, I should account for the work of the spring and the work of the weight. For the work of the spring, nothing changed because delta L1 is the same and delta L2 is the same. So the work of the spring I used before will be the same here, 0.5 K times 0.7 square minus 0.5 K times 0.6 square. But what will change now is the work of the weight, because for the weight, y1 is 0.3, but y2 is only 0.4. Okay, so for the work of the weight, it's minus w times y2 minus y1, which is 0.4 minus 0.3. Okay, equals to, from the other side, to the kinetic energy, which is half times mass of the plate, of the box, sorry, which is 2. So minus half times m, which is 2, times v squared. So the only unknown in this equation is the velocity. So I can calculate the velocity of the block when it will leave the plate. Okay. Any question on this? So hopefully we meet next time. So next time we will finish this chapter. This is a very simple chapter. Okay, and for the remaining sessions, we'll do a revision. Bye bye.
Thank you, Doctor.
Thank you, Doctor.